Okay, guys, so last time we started doing the derivation of the first principle of thermodynamics, which I told you this class is called thermodynamics. So the first equation we write over here is summation of forces equals to ma. Okay, you might follow, don't follow, but here to here, the only thing we did was to rewrite the equation of the form of work and kinetic energy. And then what I say is that this is the work, and we can break the work into three different parts. One, which is the work done by conservative forces, the one we still need to do today. The other one is the work done by all the other forces that basically, I think I mentioned at the end, that would be mostly pressure, okay? And then the other one is the work done by friction that we don't know how to calculate it, but we know that when you have friction, what's happening? You generate heat. So whatever work you created should be kind of proportional to the amount of heat that is generated. All right? So this is the equation we have. So work equal to change in kinetic energy. All right? And we stop here for the work done by conservative forces. So let me go to the next page. All right, page 11. Okay, so here we're going to look at the work done by conservative forces. Okay, at the undergraduate level, when, I'm going to talk about me, I don't know about the other professors, but when I do a derivation, it's because I think it's important for you to understand where everything comes from, but I don't expect you to know the derivation. Okay, only thing I expect is that you follow it, but that at the end you understand the final equation. Okay? The thing is that I don't like to give you an equation like, okay, this is the recipe, go and apply it. I want to show you that everything in engineering comes from somewhere, no? And the way to solve the problem is always the same way. I'm saying that because now I'm going to probably say a couple of things that might be a little bit on top of your head, okay? But it's not important. I think you're going to understand that. So what I'm trying to say is that what is a conservative force? So mathematically speaking, a conservative force is defined as, if you can rewrite the force as the negative of the del operator of a potential function, and now you're going to see why they call potential energy because of this, okay? So this is the del operator that basically is equal to what? Partial x plus partial y plus partial z, no? I think you have seen it, you've probably seen it before in one class. I guess probably calculus 3, I'm guessing, something like that, okay? Yes, but the function of the operator here is doing the gradient, but here I'm just calling del operator because it's the letter of that letter. But yes, this is doing the gradient. Okay. And then phi is a potential function. Okay. So now you're going to understand why of the term potential energy. So for 1D, so for the sake of simplicity, let us consider 1D cases. So for example, this will mean what? F for 1D should be equal to what? Minus partial x of a potential function, no? Yeah, for 1D. Okay. Okay, so you're gonna see what they call it potential energy. So what are the two potential energies that you are familiar with? What would be the potential energy due to gravity, and the other one will be the potential energy of a spring. Yeah? So what is the potential energy of a spring? It's 1/2 kx squared. Yeah? So let's look at it. So let's look here, potential. So let's see. I don't like the term potential personally. So I'm going to look at work done by spring force. So what is the force of a spring? So let's see if I have a spring here. If you have a spring here and somebody pulls to the right, what's going to be the force of the spring? Opposite direction, same magnitude, and the value will be kx, where k will be the spring constant, no? All right? And if you want a bit detail, this will be your current system. So if I really want to be detailed, what should be really F of spring? Magnitude kx, but it's in the negative direction, so it should be equal to minus kx, no? All right? So now, okay, so now let's say the potential energy, instead of doing the derivation, we do it, I give it to you. So the potential energy. But personally, I don't like to talk about potential energy. I like to call it work done of a spring is given by what? So phi, let's call it V over here, potential energy is equal to what? 1/2 kx squared, no? Yeah. So now let's go and substitute over here. So what would be partial of V? So partial phi partial x would be equal to partial V partial x. This would be equal to what? 1/2 times 2 kx, no? So this is really equal to what? Kx, correct? So let's say substituting into this equation here, F equal to minus partial of phi partial x. What do you get? F equal to minus kx. And what is minus kx? Is the force created by spring, no? Which is the force of the spring. So here, again, if you want to, you can call it potential energy. I don't like it because really it does not exist potential energy. Because really, what is it? It's work done by the pressure, work done Okay, so 1. And now, what is work? Work is what did I use? ds or dr on the previous notes? ds, which is what? Force times distance, no? So what is the work done by the spring force? What is the value of the force? Minus kx. How much will it be moving? Dx, no? So if you integrate this, what do you get? Minus 1/2 kx squared, which is what? This is the, what we say was the potential energy. But you see that really, physically, what we call potential energy is the work done by the spring force. Why do they call it potential energy? Because it happened that the force created by the spring force satisfied this equation, so the force is said to be conservative. Okay? So if it's conservative, it means that the force can be written down under the form of a potential. What is the value of that potential? Is 1/2 kx squared. So that's why people ended up calling potential energy, because now you're going to see we're going to move this term to the other side of the equation. But it's no such thing as potential energy. It's really work done by a conservative force. Okay? But again, was this complicated to follow? No, okay. But if I ask you to redo it, probably it would be a different story, no? All right, so now what is the other type of potential energy we are familiar? Is the work done by gravity. So it would be identical. So work done by gravity so what is the expression for the gravitational force? Is mg, no? Okay. So again, look at it. Every time I do any type of derivation, what do I do first? A figure, and then I write down one equation. That's the way you're going to solve all the problems. So 1D, if I do some type of little reference frame, let's say under this form. So let's say here's position 1 or 2, and then it moves over here. Okay. So this will be y1 or y2, y1, but really this would be h, and if I plot the force, what will you have? mg, no? All right. So if you want, I'm going to change a bit the order of the derivation that I did before. So if I ask you, what is the work done by the gravitational force? Would be work is equal to what? Forces times distance. Okay? So in this case, what is the value of the force? It's on the figure. What is the value of the force? mg, no? And it's actually going down, no? Yeah, so we could say it's equal to minus mg. We can integrate this, and here is moving in what direction? I mean, let's say this is just moving in one direction. The 1D would be in the y direction, no? So the variable here will be dy, and it will integrate this between y1 and y2. But what is y2 minus y1 is just h, no? So if you do the integral of this should give you what? Minus mgh. Or if you want, minus, to be, so we can do it, make it work, would be minus mgy, no? All right. So if we say that the potential energy slash function phi equal to v equal to minus mgy, if the gravitational force is conservative, then what needs to happen? You need to satisfy the conservative equation, no? Which in this case will be F equal to minus del of phi of V. In this case will be, what is the variable? It's moving on the Y, 1D. We can put here phi of V. And this will give you what? F to be equal to minus partial Y. What is the value of the potential function energy we use? Minus mgy, which this is going to give you what? F equal to mg, no? So basically what happened? We have proved that the gravitational force and the force of a spring are conservative. All right? So we can see that, so here, summary, and also pay attention that you see the potential function, or what you would like to call potential energy, is equal to the negative of mgh or mgy. And in the previous example, the energy was equal. We assume phi to be, oh, maybe change this. It should be, put a negative sign over here, okay? Because the force, no, but leave it that way. We prove here that was negative. This is negative, okay? It's fine. So summary, we say that F of the spring, Kx, and F due to gravity, mg, are conservative forces. So that implies that you can write them as a function of a potential function. Okay? And it happens that the work done by spring and gravitational forces is what? Is what we call work one, no? On the three different ones. So what is the work done by the spring? We say that it was equal to what? Negative 1/2 kx squared. And the last one, what is the work done by the gravitational force? Minus is right here, minus mgy, we could just say minus mgh. But basically, what you can say at the end is that the work done by conservative forces will be equal to what? The negative of the change in potential energy, where PE here will be, I use potential energy because I know you like it, so otherwise I will never put it there. Okay. So again, did you follow? I'm not expecting that you fully understand what's going on, but did you kind of follow? I don't think it's that complicated. Again, you don't have to know how to do that. The only thing you know is what's going to happen at the end. So page 13. So let's see. So recalling the equation, I'm basically talking about this equation here, all right? That we had what? So the work was equal to the change in kinetic energy. And we said that this term over here, which is work, had three terms and three, no? So let's see. Where here we say that work of 1 is the one we just derived, was equal to what? The negative of the change in potential energy. Work 2 is the one that we said we leave as the general work, that in most cases will be the work done by the pressure. And work 3 is the work done by friction, but if you want to make it more general, the work done by all the forces that are non-conservative. Okay, we cannot calculate what is the expression for work, but we know that they create that if you have friction, you generate heat, no? So we say W3, work 3, will be equivalent to heat. So if we combine all this stuff, what do we have? So the term on the left-hand side would be equal to what? Minus change in potential energy plus work plus Q equal to the change in potential energy. Again, not important that you fully understand the derivation. I mean, fully that you could do it on your own, but that you understand the steps that I do. Okay, now I can rewrite this as what? Let's say write as Q plus work will be equal to what? Delta change of kinetic energy plus change in potential energy. And that's why they ended up calling potential energy, because they always move it to the right-hand side. So instead of saying change in kinetic energy plus change of the work done by the quantitative forces, okay, they say, okay, this is also a potential function. This is energy. Let's call it potential energy. But it is not such thing as potential energy. It's work done by a quantitative force. All right, so we're almost done. Now, the last term, I cannot derive it. I can only explain it to you, but it's not complicated to understand it. So there is a third energy term known as the internal energy. Okay, and this term will be known as the change in internal energy. They use the letter U. That represents the energy change needed at the molecular level to go from one state to another. So again, it's easy to understand. So for example, what happens if you want to transform water, let's say, into snow, okay? Instead of ice, let's say snow, okay? So you're gonna apply cold, okay? You're gonna put it in the freezer or whatever you want, or let's say you have normal water and outside is freezing temperature, you throw it out and it might come up as snow, it might come up like little ice, no? But what is the difference between liquid water and liquid ice or snow? The water is liquid, you get wet, the other one becomes solid, but what's happening internally? The molecular structure of the water changes, no? Okay? And for the molecular structure of the water to change, energy is used. Okay? What is that energy coming from? It's coming from the substance itself. All right? So in order to change its molecular geometry, if you want, the substance needs to use some of its internal energy. Does that make sense? Okay? So basically, so that the above equation becomes what? Become Q plus work equal change in kinetic energy plus change in potential energy plus the new energy that I put over here, change in internal energy. Or I can write this heat plus work equal change in energy where the total change in energy equal to the change in kinetic energy plus the change in potential energy plus the change in internal energy. Okay, and this equation here is the first principle of thermodynamics. Okay, so I want you to realize over here that what was the starting equation? This equation here is actually equivalent to what? Summation of forces equals to MA, no? Yeah, we just brought it on a different form, okay? So I derived the equation. This is the correct equation, but now there is something between 50% of the books and another 50% of the book. They use a slightly different notation for this. I mean, they just switch the sign. And I will explain why, okay? Or you will understand why. Probably later on. So I'm going to write over here. So attention. All right, so I did the derivation. What I did is correct. Okay, so attention. So if you want, textbook notation, and then let me put over here class node notation. Maybe I should have reversed this too. Basically, what is the equation we're going to use over here? Change in energy. So basically, on the class node notation that I use, I mean, it's not that I use, it's the correct derivation. What happened is that they change it because it's a little bit easier to understand something that comes out later. But basically, this is your system. If you put heat into the system, so whatever you put in is positive, okay? So let's say you put heat in, this is positive. If you put inside your system work is positive. If the system gives heat, the value should be negative, and if the system gives work, it should be negative. Okay? The textbook uses the following notation. So for them, this equation is going to become what? It's going to become Q minus work equal to change in energy. So in this form, what would be their sign convention, or yeah, the notation, the sign convention? Okay, so the Q remain unchanged. So Q going in will still be positive. Q coming out will still be negative. But now what's going to happen for the work? It's going to be switched, no? So work coming in or done on the system would be negative, and the work done by the system will be positive. So mathematically speaking, from the derivation point of view, the one we just did in class is the correct one. All right? But because other homework problems are coming from the textbook, I'm going to continue from now on the class notes using the textbook notation. Okay? So, and I will explain why. Maybe let me explain now. Why do they use this? Okay? All right, so let's say for a cycle, let's say the cycle of your engine. Right now, this might not say too much, but the important thing is that, all right, so let's say this will be P and V. Imagine this is your piston, but what's important over here is not the figure, is this. What happens if you start at one point and you go through different processes and you stop at the same point? In that case, what would be the change in kinetic energy? If you start at one velocity and you end up at the same velocity, it will be 0. If you start at one height and you end up at the same height, it's going to be 0. If you end up at a certain value of internal energy and you end up at the same value of internal energy, what would be the total change in energy? 0. Okay? So in that case, you have change in energy equal to 0. So that, what do we have? Let's say if we use the textbook notation, and this is the reason why they do it, will be equal to 0, which will give you work equal to heat. Okay? And if you use the class node notation, what would you have? Work Okay, let's say it would be, I mean, to make it correct would be what? What should we have over here to make it be correct? Negative work should be equal to Q. So basically what happened is this, is that I think is from the intuition point of view, what is more logical to say? Okay, if I put heat into a machine, that heat is going to become work, correct? Okay, so in that case, in order for simplicity, it's a lot easier to see the equation. If I want work, the amount of work I can get from the system is equal to the amount of heat that I can put in the system. But in that case, what happened is that the Q coming in needs to be positive, but also the work coming out needs to be positive. Okay? However, if we use the 100% mathematically correct equation, this will give us what? The amount of heat going in will be positive, needs to be equal to the negative value of the work, because this is actually the one coming out. Yeah? All right. So that is the reason why some book decided to take this notation, because it's a lot easier to explain this, no? Does that kind of make sense? Okay. So now I'm just going to write down. This should be page, I guess 14. Page 15. So from now on, the below form of the first principle of thermodynamics is used. So basically, we're going to use heat minus work equal to change in energy, where the change in energy is change in kinetic energy plus change in potential energy plus change in internal energy. Okay, so even though I did the derivation for the positive side, we're going to remember the first principle of thermodynamics under this form, okay? Q minus work. Personally, I don't like it, but since it's the way they did it in the textbook, I don't want to create issues for the homework, no? All right? Okay, so previously, like maybe a few minutes back, when we derived this equation, what did we say W was going to be for? We said that probably this W here is going to take into consideration the work done by the pressure. Okay? All right? So let's see what would be. Let's look at the pressure. I think I already derived the pressure initially. Yeah, I'm pretty sure I did it the first day, but anyway, let's do it again. So pressure is force over area, or P equal F over A. Okay, so what did we do over here? Remember, we say what is the work done by the force of the spring? And we say the work done by the force of the spring ends up being equivalent to 1/2 kx², no? What is the work done by the gravitational force? We ended up knowing that that was equal to mgh, and that is what we call at the end potential energies. All right? So now, what is the work done by the pressure. Okay, so like before, first thing we need to do is a figure. So be careful because my figure might not be that good. So the main thing that pressure is used is for piston cylinder system. So let's say we have a piston over here. So inside your system here, let's say you have a gas, okay, probably air, all right? And in this case, let's say that the gas is going to expand. So what's going to happen to the head of the cylinder? It will move up, no? So let's say this is position 1. This is position 2. Okay, I'm not going to do it in this view. I'm going to do it in a small one over here. But if you look at the piston in 3D, basically, maybe I should have done the figure here. The pressure is equal to the total force now acting over here divided by A. All right, and let's say this is moving a distance dy. Okay, so we're going to look at work done by the pressure will be equal to the integral of the force of ds. So basically force times distance. Oh, something I think I forgot before to discuss with you is that what is the sign convention for work? Because I think we don't discuss it because it worked out perfectly with the equations. But what is the convention for positive or negative work? So I think it's easy to understand. So work is force times distance. So let's say you are pushing a table uphill. If you're moving uphill and the table is going up, that will be known as positive work. Okay? If you are pushing the table up, but you and the table are moving down, so basically the direction of, so if you move the table up, your force is on the same direction as the displacement, no? Yeah, as the ds. If when you go up the hill with the table, the force is going up, but the overall motion of you and the table is going down, it is in the opposite direction, okay? So when the force and the deformation are in the same direction, is known as positive work. If the force and the deformations go in opposite direction, it will be known as negative work. So for example, what was the work done by the spring? It was negative, no? Because what happened to a spring? If you push it, it's going to try to push you back, no? All right? So it's opposing the motion. So actually, here, a piston cylinder assembly is exactly the same thing. If you push down over here, what is the gas going to try to do? To push you up, no? And if you try to move it up, you're going to create a bit of vacuum. So what's going to happen? It's going to have a tendency to go down. Yeah. So we agreed that the work done by the pressure is going to be, no matter what, negative. And that's another thing that the book is going to change. But I mean, but again, it should be negative. Now, what is the value of the force of the pressure? Force of the pressure is equal to P times A, no? This is the force from this equation. F equal P times A. Or from here, F equal P times A. So the force created by the pressure is equal to P times A. And now, in what distance is this moving? It's moving on the, let's say here, let's call this y direction. Okay? Now, what is dA dy? So what is A times d dy? So area times change in height is going to be volume, no? Yeah? So this equation, this really becomes dV, and my V this way is volume. So at the end, we have that the work done by the pressure is equal to minus integral P dV. And now, so what happened? Because in this expression, they changed the same for W. What should we do also for this one? Change the sign, no? Maybe, okay. All right, so I'll write it down. So all right, so let's see, let's go over here. Summary of textbook notation. So we have Q minus work equal to change in energy, where if this is work done by pressure, in the textbook this is going to be positive PdV. That's it. I don't think there's more changes in signs, okay? There's another thing on the textbook that I don't like, that I don't use, but not going to be until the end. So basically, that's the two equations by now that you need to memorize. I'm not going to ask you to derive them, okay? So you need to memorize these two equations. The first principle of thermodynamics, and what is the equation for the work done by the pressure. Okay? So now, we're going to have different cases of the work done by the pressure. So first, we're going to look at work done by a constant pressure. So basically, what does that mean? P equal to a constant. Okay, so the equations we are doing now, you don't have to memorize them. You can derive them in 2 steps just by knowing this equation. Okay, so let's just substitute over here. So in this case, what would that mean? Work for constant pressure equal to P dV. We're going to integrate between an initial volume and a final volume V2, so V1, V2. If P is constant, this integral will be equal to what? P V2 minus V1. Yeah? Was this complicated? Okay, so this is the work done by a constant pressure. Now, mathematically, why did somebody invented the integral sign? So if I do a figure, this will be equivalent to what? Let's say this is P and this is V. If the pressure is constant, what does that mean? It's just a straight line. If this is V1 and this is V2, what is the physical meaning of taking the integral? You find the area. So really, the work done by the constant pressure is just the area under the curve, no? Yeah? Okay, and maybe we have time to do one more. Now, these other cases, which is work done, so there's only one more case, but it has two different parts. So work done by a polytropic process. So what does polytropic means? Polytropic means that PV to the K is equal to a constant. Okay, so I'm going to write it here, polytropic, since this is new. This may be one equation I'm going to have to memorize again as well. PV to the K equal to a constant, where K here is a gas constant. And basically that K for aerospace is actually called gamma, but what is the physical meaning of that constant? Is that different gases are going to compress differently, no? Okay, so if you look at air, I think it's 2.4 or 4.2, I think it's 2.4, but for hydrogen, it's probably going to be another value. So really what this K indicates is the compressibility of that gas. Okay, you don't need to know that, but we need to know this is a polytropic process. So in this case, PV to the K equal to constant. Okay, so we have two cases. One case would be to say that K equal to 0, which will be PV to the K equal to PV now. And the other one would be to say PV different than 0. So which one you want to do first? PV equal to 0 or PV different, or the K equal to 0, the K different than 0? Right, so let's say case 1, I decide if K, okay, let's do different than 0, that's it. So in that case, what do you have? PV to the K equal to a constant, which means that the pressure is equal to a constant divided by V to the power K. All right. So in that case, what is the work done? By pressure. By pressure P equal to C V over K. So if I rewrite the expression, what is work? We just said that work done by pressure will be equal to what? PdV, no? That's what we had over here, no? PdV. Okay. What is P equal to? P is equal to C over V to the power K dV. Okay. I'm going to rewrite this a little bit differently to make it easy for you. If I leave it this way, 3/4 of the class don't say anything. If I write it just differently, everybody knows how to do it. So let's say C is a constant. So what can I do with a constant? I can put it outside. Can be anything. This will be integral. And now if I put here, instead of V divided by K, I call it V minus K dV. Okay. Now, what is the integral of x to the n dx? What is the integral of that? It's n to the n plus 1 divided by n plus 1, no? Okay. So what would be the integral of this? The integral of this should be C integral of V minus K plus 1 divided by minus K plus 1, no? Between, maybe I forgot to put that, we integrate between V1 and V2. V1, V2. Okay. All right, so over here now, I'm going to write this a little bit differently. So I hope you follow. So let's first do, I'm going to put outside, this term over here is going to be constant, no? So let me just put it outside. I'm going to put 1, and instead of minus K plus 1, I'm going to call it 1 minus K. Okay? Now is when you need to be careful of what I'm doing. I'm going to do it in 2 steps anyway. The C, I'm going to put it back inside. So if I first do V2 over here, this should be equal to what? C V2 2 minus K plus 1 minus C of V1 minus K plus 1. Okay, so now here is, I mean, it's not the trick, but it's to understand, and the first time you don't think about it, but what is a polytropic process? It's PV to the K equal to a constant, no? Yeah? So a polytropic process is PV to the K equal to a constant. So what does that mean? That means that C can either be equal to P1 V1 to the K, but it can also be equal to P2 V2 to the K, since it's a constant. All right? So what I'm doing here, I'm going to take advantage of this, and I'm going to say, you know what? In here, this C is going to be equal to P2 V2 to the K, And in this case, the C is going to be equal to P1 V1 to the K. So that at the end, since we have time, I'm going to write it down. You're going to have 1 over 1 minus K of P2 V2 to the K times V2 to the minus K plus 1 minus P1 V1 to the K V1 to the minus K plus 1. So at the end, what's going to happen is that this term here, minus K, is going to cancel with the K, no? This minus K is going to cancel with this K, and we're going to be left over with V2 V2 minus P1 V1. Okay, so the work done for a polytropic process when K is different than 0, and maybe here, can it be 1? No, because you will see it will be 0, no? So it becomes infinite. So really, that's why I didn't want it to put, but if I wanted to be accurate here, I should say for K element of all the real numbers minus 0 and 1, no? But I think it's not going to help at all, no? Yeah? Okay, so let me just leave it that way, okay? So if you want to put different than 0 and K different than 1, okay? I was going to write it differently, but let's put it that way. Okay, and this is the last thing I'm going to do today. If I needed to plot this, so basically this would be PV. Okay, polytropic, the line can either be concave or convex. Okay, it doesn't matter how you plot it, but let's just say you go from 1 to 2 and do whatever you want. I'm going to do it this way, but it could be the other way. All right. So again, as we did before, what should be the work? Will be the area under the curve. All right, so now the next case we need to solve is when K is equal to 1, no? Yeah, to see what happened. And that will be the last expression we have for the work, but I don't think we have time to do that. So we'll do it next week. All right, so I will stop the video over here. And so have a nice weekend, guys. Start working slowly on the homeworks. I think the first homework is only 2 problems, but